So I'm doing another Maclaurin series video here, and I chose this function y equals 1 over 1 plus x because we had a lot of fun with this function when we were talking about the binomial theorem and the generalized binomial theorem. And some of you asked, well, why does it work? Why can we generalize the binomial theorem? And if you use Maclaurin series, that's one way to justify the generalized binomial expansion of this sort of thing right here. So I'm going to come at it just like I'm trying to find a Maclaurin series. And so what I would do is, of course, rewrite this in a different format. So 1 plus x to the negative 1. So then you can just drop that power in front. And, you have to use the chain rule, but the derivative of the inside is just 1. So it's not so bad. So then y double prime is going to be positive 2. 1 plus x to the negative 3. Y triple prime is negative 6. 1 plus x to the negative 4. Y quadruple prime is 24. 1 plus x to the negative 5. And I want you to notice something. We talked a lot in that first chapter about how there was a factorial going on. And I hope you can see that the coefficient is a factorial. We have, in this initial spot here, we've got 1 factorial, then we got 2 factorial, 3 factorial, 4 factorial, 5 factorial. It's switching positive and negatives, but you can see the factorial pattern going on there. Now, what I'm going to do, because it's a Maclaurin series, is plug in 0 to each of these. And let's just write that value in purple. So when we had 0, what did we get? 1. When we had 0, what did we get? Negative 1. When we plug in 0, we get 2. When we plug in 0, we get negative 6. When we plug in 0, we get 24. When we plug in 0, we get 120. So that's going to be the values that I use to construct my Maclaurin series. So just like before, please watch as the approximation improves. We start with y equals 1, hits it at 1 point, really crappy approximation of the curve. Then we take 1 and we can write plus negative 1, or I can just write minus x. And you can see it's a slightly better approximation of the curve there. At least it's touching the arm that's on the right side of the graph. Now let's go to the x squared term. So I need a 2x squared, but divide that by 2 to match the power. You can see the parabola kind of hugs it a little bit there. It's not great, but it's better. Next one, we're going to go minus 6x to the third divided by 3 factorial. Then the next one is 24x to the fourth divided by 4 factorial. And I can continue this as long as we want. X to the fifth divided by 5 factorial. And you can see here one of the limitations of the Maclaurin series is that when you have an infinite discontinuity, like here we have the vertical asymptote at x equals negative 1, you're not going to get a polynomial that's going to jump across that discontinuity. And so in the earlier videos, I talked about a function being sufficiently nice, like e to the x or sine or cosine. Those have no infinite discontinuities in them. And so the Maclaurin series works a lot better. But we saw with e to the x that there was no way the polynomial was going to have the horizontal asymptote that e to the x has. Same idea here. We're not going to get the horizontal asymptote. We're also not going to get the vertical asymptote. But the more terms that we add on, it still becomes a better approximation of the function. And one other thing I want to point out is that, like I mentioned, the values of the derivative are a factorial. And in a Maclaurin series, we always have the factorial in the denominators right there. And so you may have remembered that y equals 1 over 1 plus x could have been expanded like 1 minus x plus x squared minus x cubed. I hope you see now how that's really just taking the values of the Maclaurin series and canceling out the things that are equal on the top and on the bottom. So there's one more example of a Maclaurin series. And there you go. Like I mentioned, if you want more examples, please just ask. I'm happy to make as many of these as you need.